So as you all are talking, you realize that even though this is normal for you, that for most of the world, this kind of conversation and information is very unusual. And I of course find it fascinating. But I have to tell you, one of my children came home one day and said, "Hey, Dad, I have somebody who's been watching The Big Bang Theory, and they want to know if that's really how science is." And he very, if you knew Dave, I mean, you can see him saying this. He said, "Well, they would say in lab that it's not so much a sitcom as it is a documentary." So, anyway, with that, we have our second recipient of the OSG David Swanson this year is Jimena González, who, despite being a physics graduate student here at the University of Wisconsin-Madison, still had to participate virtually in the OSG school in 2021. That's how it was. I would like to thank her advisor, Professor Keith Bechtel, and other members of his lab for joining us to hear her presentation. Since attending the school, Jimena has used computing capacity in the Open Science Pool, plus applied her learning to leverage a similar system down at Fermilab, about 300,000 total hours of computing. She will tell us how this has made possible her research into gravitational lenses as a tool to explore dark energy and fundamental properties of the cosmos.
Okay, can everybody hear me? Perfect. So yeah, my name is Jimena, and I am a PhD student here in physics. And I'm very happy to talk about how I implemented OSG resources to excel my research, in which I'm searching for strong gravitational lenses in the dark energy survey. Okay, try again. Oh, perfect. Okay, so I'm going to start with an outline of this talk. In the first part, I'm going to talk about everything that is all the basics about strong lensing. We're going to talk about what it is and how we can use it to do science. And then I'm going to give some context about the challenge of searching for strong lenses. In the next part, I'm going to talk about the project workflow. So here we're implementing machine learning. And the first step to do this is that we need to create a training sample so we can train the machine learning. Then in the last step, we're going to do the complete search. So in this section, I'm going to talk about all the computational limits that I had in every step. Next, I'm going to give some context about what I was doing before I attended the OSG school and how I transitioned every step of this and used what I learned in the OSG school to excel my science. Finally, I'm going to talk about the quantitative impact that this school had in my research and how I was able to expel the limits of what was available for me. So I'm going to start with the very basics of what is a strong lenses. So strong lensing happens when an astronomical source is emitting light and is located behind a foreground galaxy. The light coming from the source is bended by the gravitational potential of this foreground galaxy. And this appears as images, multiple images of the same source that sometimes are magnified. So this can look different depending on the source, on the size of the source. If you have a point source, for example, of an exploding star that is very small, you will see multiple images that are separated from each other. But if you have an extender source like a galaxy, these images get strongly distorted and you see huge arcs of light. Now, the observables, which is what we can measure from these systems, will be the position of these images of the source in the total image, how the relative magnification between those images. And if you, for example, imagine that this is an exploding star, there are some paths of light that are going to be shorter than others. That means that some of these images are going to appear brighter than the other ones. So you can measure a time delay. All of these measurements are related to the mass distribution of this galaxy. So you can use strong lensing to study elliptical galaxies, for example. But what I'm very interested in is to study dark energy. And then if I were to put this into simple words, I would say that studying the nature of dark energy will allow us to understand the ultimate future of the universe. So that's why I care about this. Okay, so let's talk about how hard is this problem. So here I'm showing an image from DES. And if we zoom in here a lot, you will see that here there is a strong gravitational lens. Now, DES covers about an eighth of the sky, which in other words is like 500,000 images of this. And in all of those images, we're expecting to find about 600 strong lenses. So this gives context about why we need to employ automatic searches for these systems. Okay, so in our research, we're implementing machine learning methods. So the first step that we need to address is to create the training sample. Here, I'm only going to focus on the positive class. Later, I'm going to talk a little bit about the negative class. So the positive class, we don't have so many strong lenses that are known. And to train machine learning, you need a lot of data. So for this reason, we need to create simulations. And then these simulations have multiple properties that are going to control like the quality of the image. So what we want is that we want arcs that are bright and that a human will look at this and would agree that they are strong lenses. And then this, what controls the quality, I'm going to call them constraints on those properties. So the computational limit is that, first of all, I need lots of simulations to train. And in other words, I would say like for 15,000 simulations, I will have to be waiting 2 days. And then the tighter I will set these constraints to have a good quality simulation, it would increase by a lot the time that I was waiting. So I was waiting about 4 days on good simulations. And then what this implies is that I couldn't experiment with many different properties for the simulations. And I had to be very thoughtful about how I was doing these constraints. The next step is the training the machine learning. So I'm not going to go into any details, but then the model that we implemented is the vision transformer, which was developed by Google. And it's a model that has about 86 million parameters. What this means is that this is very time consuming to train. And it was taking about 3 days on my personal laptop. And as you would imagine, increasing the training sample would increase the time that you need to train. So every training run was a huge commitment, and there are so many parameters that you can modify when you're training. You can modify your training sample, but you can also modify little parameters in the model. And then the next step, and my main concern was the total search. So we needed to process about 200, this number is wrong, it's actually 230 million images, which is about 1 terabyte of data. And I never did the math for my personal laptop. I did it just for this talk. It was about 7 years. And in the cluster that I was running, it was about 4 years and a half. So then I was concerned with the typical question that you have, when am I going to graduate? So I wanted to give some context about what I was doing when I was preparing my application for the OSU school. So I was mostly spending my time doing simulations with different properties, and then I was training. And all of this, only one experiment will take 2 weeks of time. And then I was also applying some of those models that were trained to unseen data. So about 8,000 images, maybe that sounds like a lot, but that's very little. That's like 0.04% of where I was going to do. So I couldn't actually, I grew to understand results, but I actually was not understanding my results because this was a little bit of data. So you can imagine that most of the time I was just waiting. And then not only I was just waiting, but I had a lot of pressure on me that if I made a single mistake, I'm wasting 2 weeks of research. And then this is not even addressing the elephant in the room that existed since we started this project, which is how are we going to make the total search? So OSG came to me and it was great. I was able to implement it in different steps of my research. And now I'm going to talk about how every step was changed. So first part is the simulations. So this fact is very easy to understand why it is parallelizable, and is that every image here is independent from each other. So I could imagine that I'm going to send many different jobs to generate different simulations. And each simulation doesn't take that long to create. It's only about 2 seconds. So when I went to implement high throughput computing, this was a very straightforward process in which I only needed to be organized. I needed to have clear, what do I need for each job? Then what do I need to get from each job? And what are the software requirements? And then on top of it, I needed to do a few modifications that are like the number of simulations that I needed from each job, which will control the time that each job takes to run, and also random set. This one was very important because I need to make sure that every job is making simulations that are different. And I did a lot of testing. And then when implemented high throughput computing, my waiting time went from about 4 days to 4 hours. Okay, then the next step was training the machine learning. And then this task was challenging because it's not parallelizable. And you can imagine that if you study with a group of friends, you're going to take an exam. Each one of you has to review all the material. So I couldn't parallelize this, but OSG resources were still very helpful. And I could run one job where I just will request one GPU. And only doing this reduced my waiting time from about 3 days to 4 hours. Okay, and then the next step, which is the total search. So this task is also very understandable why it is parallelizable. Every image is independent from each other, and I don't care which images get seen first. And then on top of that, DES is already divides the data into 10,000 pieces of similar size. So the data was already divided into what we call tiles that are about 10,000. And processing each tile doesn't take that long. It's only about 4 hours. So this was perfect to implement for high throughput computing. And then the challenge that I faced is that at the time of this analysis, the data was not public. It was very heavy. And because it was not public, I couldn't use the normal transferring methods that we use in OSG. So I had to find a way to use what I had available. And it turns out that I had available something that was great. I just didn't appreciate it before attending OSG. And this is the Fermi grid. Then in this cluster, the syntax is different, but in the back end, it uses CHT Condor. And then because it was the same idea, same concept, I was able to get this running very quickly. So I went from an idea that I will have to wait for 1.5 years to only 3 days. It's actually less than 3 days because I did it on a weekend. And this was amazing. And here I wanted to put in only one slide how every step in this workflow was affected by OSG. So I went from waiting 2 weeks for only one experiment to waiting less than a day. And then the complete search was amazing because it allowed me to search through many different images while I was testing. And all of this allowed me to think about things methodologies that they didn't even occur to me before because they were not available. So one of for context, the main challenge of these searches is that there are many astronomical objects that can resemble strong lensing features. For example, there are spiral galaxies or ring galaxies. And then they make that the purity rate of current searches is about 1%. So that means that from 100 images that a machine learning model says that are positive, only one is actually positive. And this is really bad, especially now that we're going to move to future surveys. We are in the era of big data. We need to improve this. And thanks to OSG, I was able to think about how are we going to improve this. So I implemented an interactive machine learning approach in which you train a machine learning model, you see how it performs on seen data, and then depending on that, you can give it feedback. And the feedback can be by changing your training sample, or you can also change features in the machine learning. And then you can do this loop as many times as you want, and stop when it reaches a good performance according to you. So then the end is that model that is going to perform similar to what you want. And then the way that we implemented this here is that we started with a very simple training sample in which we only had a positive class and a negative class. After training and applying this to real data, we noticed that there are so many spiral galaxies. So we needed to include that. I created a new class for these spiral galaxies. And then I trained again. and I went to see what was happening. And then I repeated this process multiple times, and at the end, I turned out that I created 9 different categories to make sure that I will increase the purity rate as much as I could. And here I wanted to show a little preview of the results. So what you're seeing here on the screen, okay, so I have about 20,000 candidates. Of course, they're from the machine learning. We need to filter them out. But here I wanted to show a sample of candidates with a very high probability according to the machine learning. Many of these candidates are actually strong lenses. But then I cannot give you a number of the purity rate here because everybody gets a different number. And they can be experts, but everybody gets a different number. So I will not give you a number, but you can see that many of them are strong lenses. And if they are not, it's understandable why they were flagged. Okay, so I wanted to conclude first by showing some beautiful lenses that I have seen, and then you can see all the different colors, different shapes, and different sizes. Very beautiful image. And I also wanted to talk about the state of the project. So this is work in progress. And right now what we're doing is that we're planning a crowdsourced project. So we're going to host on Zooniverse, which is a website, a way for people to label images. And anybody can log in this website and help me extract the most compelling candidates. If anybody is interested or knows people who may be interested, contact me. I think I am the only González attending this. So maybe that will help remember me. And then I am still not done with OSD, and I'm very excited to keep pushing the boundaries. So in the next steps, I'm going to be characterizing these candidates that we have. That means studying the mass distribution of the candidates. And finally, I wanted to say thanks to all the OSD consortium, all the teams, especially to Ian, team, and Ken that I still haven't met, but Ken was very helpful for Fermilab, in the Fermilab cluster. And I'm very grateful that I was able to focus on the science and not be limited by the computational resources. So thank you.